Everyone. This is a risk assessment presentation for the course ELI 9110 at University of Western Ontario. This course is taught by Professor Lucas Tung, and we are group number 11. We'll be presenting an analysis of an anaerobic digestive system. According to Brisbane, by 2050, the world population is expected to grow by 40%, and the demand for food and fiber is expected to grow by 70%. The Canadian government offers many investment programs with the goal of distributing funds to support the agri-food industry. Such programs allow the industry to better position itself through disease prevention, R&D boost, international branding support, international market diversification support, and adaptation to new international agreements. Some farmers have been taking advantage of some programs to implement anaerobic digestion systems, which is what we're going to analyze in this presentation. What is a anaerobic digestion system? The anaerobic digestion of manure in agri-food byproducts system is the process by which organic materials in a enclosed vessel are broken down by microorganisms in the absence of oxygen. And you can see here a picture with an example of such installation. AD reactors contain complex microbial communities that break down or digest the waste and produce resultant biogas and digestate the solid and liquid material and products of the AD process, which is discharged from the digester. Various kinds of feedstocks can be used in anaerobic digestion, such as manure, municipal wastewater, municipal solid waste, fats, oils, and greases, food scraps, and sludges. The importance of AD systems. An AD system can produce many benefits for the owner, including production of renewable energy, such as gas and heat, diminish odors and lower presence of pathogens in the manure. Uh, Greenhouse gases are also captured and transformed into useful subproducts, effectively reducing the emissions of the farmstead. Nutrient-rich fertilizer can then be used and/or sold locally. This also improves local waste management. And on top of that, local farms can also get rid of their waste for a fee and buy back the fertilizer produced by the AD system. Farms is such an example. This farm is located in Ambro, Ontario, and the farm is it's a family dairy farm with 250 cows, which in 2012 installed a 500 kilowatt anaerobic digester system for on and off farm organics. The feasibility was asserted through two programs, the Ontario Renewable Energy Standard Offer Program and the feed-in tariff programs. Uh, Added value to the farm without the need of increased farmland was a big bonus from these programs. Um, so in 2013, the farm finished installing the first part of the project, which was 250 kilowatts. Then in 2017, the remaining 250 kilowatts capacity was installed. After the analysis, the Canadian Biogas Association stated that the digester is fed 10,000 tons of off-farm organics and 20,000 tons of on-farm organics a year, including livestock manure, apple waste, potato waste, groceries, store fruits and vegetables, chicken processing byproducts, grease, trap waste, and occasionally byproducts of ethanol production. In addition to biogas, the other end product of the process is the digestate, a nutrient-rich slurry. The digestate solids and liquids are separated, and the solid portion is used for bedding in the dairy farm barn, and the liquid portion is applied to the farmland.
Starting from the general overview of the anaerobic digestion system, we have a flow chart which states that how the organic waste is converted into biogas and valuable byproducts. So let's break it down by step by step. So this process begins with the collection of organic waste. This waste can come from various sources including food scraps, agricultural residues, and animal manure. The collected waste is then moved to the organic waste handling system where it is stored and prepared for the digestion process. Now, the heart of the system, which is the anaerobic digester, here the bacteria break down into the organic matter in the presence of oxygen, producing biogas, a mixture primarily composed of methane and carbon dioxide. Now, apart from the biogas, anaerobic digestion process also generates valuable byproducts. These byproducts are separated into solid and liquid components. So where solid byproducts such as compost, soil amendments, and bedding materials can be used to improve soil health and enhance agricultural practices. On the other hand, liquid byproducts including fertilizers and flush water can be used to fertilize crops and support plant growth. Once the biogas is produced, it moves to the biogas handling system. This system collects and processes the biogas, preparing it for the further use. The biogas can be used to generate electricity and heat, providing a clean and renewable energy source. Additionally, when processed and refined, biogas can be used as a transportation fuel, replacing traditional fossil fuels. To optimize anaerobic digestion, several key parameters must be considered, starting from retention time or the length of time organic matter stays in the digester, which typically ranges from 15 to 60 days. The organic loading rate, which is the amount of organic material added per day, which is crucial for efficient operation. Maintaining an optimal pH is also crucial, which ranges between 6.8 and 7.2, essential for microbial activity. Next, volatile solid reduction measures how effectively organic matter is broken down. And lastly, the temperature plays a significant role with the mesophilic bacteria, which ranges from 30 to 37 degrees Celsius. For thermophilic, it's 50 to 60 degrees Celsius. And lastly, for the psychrophilic, below 20 degrees Celsius, affects the digestion rates. Now, ultimately, the performance of an anaerobic digester is evaluated through key indicators, starting from biogas production, which is measured as the volume of biogas produced per unit of organic matter, as is a primary metric. Secondly, the digested characteristics, including solids, content, nutrient level, and pathogen presence, are also important factors to consider. The effective management of an anaerobic digester requires diligent monitoring and control. Regular checks on key parameters such as temperature, pH, and biogas production are essential for optimizing the process. By adjusting feedstock, temperature, and pH, operators can fine tune the system for maximum efficiency. Anaerobic digestion contributes to environmental sustainability in several ways, as it captures methane, a potent greenhouse gas, preventing its release into the atmosphere. The resulting digestate can be used as a valuable fertilizer, reducing the need for synthetic alternatives. Proper management ensures this minimal environmental impact. To assess the economic viability of an anaerobic digester, energy balance is crucial. This measures the ratio of energy produced from the biogas to the energy consumed for operations like heating and mixing. Positive energy balance indicates the system is generating more energy than it consumes, making it economically attractive. Now, we will see the types of anaerobic digesters designs starting with a covered anaerobic lagoon. A covered anaerobic lagoon is a large open pond covered by a flexible material. This cover traps the biogas produced during the digestion process, primarily methane, which is then collected and piped to a combustion device for energy generation. The lagoon itself is divided into at least two cells, allowing for continuous operation while one cell is being cleaned or maintained. This diagram shows the flow of materials through the system where the organic waste or digester influent enters the lagoon, then the biogas produced rises to the top and is collected through the biogas pipe. The treated organic matter or digested influent exits the lagoon after completing the digestion process. And as we can see the image, which includes a smaller diagram with a covered anaerobic lagoon in a large scale setting with multiple lagoons and a biogas collection system. Next is plug flow digester, which is a type of anaerobic digester commonly used in dairy operation. It's particularly well suited for handling manure collected through scrapping. The diagram shows a long covered tank with a flexible cover, where one end of the tank is assigned as the influent area where the organic waste enters, and the other end is the effluent area where the treated material exits. The waste matter moves through the tank in a plug-like fashion. That's why it's termed as the plug flow digester. A cross-sectional view of the digester is provided in the diagram showing the internal structure. The biogas produced during the digestion process is collected under the flexible cover and stored in a biogas storage area. We can see a small image at the bottom which showcases a real-world example of a plug flow digester with a flexible cover. Next is the complete mixed digesters, where the system consists of two enclosed heated digester tanks built on a concrete pad. Each tank is equipped with a mechanical mixer to ensure consistent mixing of the digester contents. Organic waste such as manure is collected in a reception pit and pumped into the digester. This digester processes the breakdown of the organic matter, producing biogas which is captured and stored under a flexible rigid cover. The biogas can then be used for various purposes such as generating electricity or heat. A heat exchanger is often installed into the system to maintain the optimal temperature for the digestion process, and the treated effluent or digestate is removed from the digester at the other end. The diagram is here can be seen the circular nature of the process as the digestate can be further treated or used as a fertilizer.
Identified risk in anaerobic digestion. Identifying risk in the anaerobic digestion process is crucial to ensuring the safety, efficiency, and environmental compliance of the facility. The chart shows the overview of the different risk categories in anaerobic digestion. The risks are organized into key areas like health and safety, environment, equipment, measurement, materials, people, process, operational, management, and external factors. Each category is crucial with examples such as health and safety risk affecting workers and the community, while environmental risk impact the ecosystem. Equipment and operational risk are tied to the reliability of machinery and processes. Identifying risk across these categories helps prioritize efforts to keep the AD facility safe, efficient, and following regulations. Fishbone diagram for identified risk in anaerobic digestion. We use the fishbone diagram to identify and categorize risk in anaerobic digestion. The diagram sorts risk into areas previously mentioned like health and safety, environment, process, equipment, etc. Each category lists specific risks such as biogas leak, land bank contamination, equipment failure, and many others. This method helps spot potential issues and their causes, making it easier to develop strategies to address them. The fishbone diagram ensures all parts of the AD process are considered, supporting a safer and more efficient operations. Impact of identified risk in anaerobic digestion. This slide outlines the impact of risk in anaerobic digestion, focusing on health and safety, environmental, and process related risk. Health and safety risk like biogas, such as methane leaks, and emission of gases like carbon monoxide, hydrogen sulfide, SOx, NOx, and other gases can lead to severe outcomes like explosions and pollution, highlighting the needs to manage these risks to protect people and the environment. Environmental risks like contamination from digestate spills and land bank degradation can lead to water pollution and soil quality loss. For processes, inadequate maintenance and emergency procedures can cause operational inefficiencies and increase risk. Let's continue to explore the impacts of risk in anaerobic digestion, focusing on operational, equipment, people, and management categories. Operational risks include climate extremes that can disrupt operations and damage infrastructure, showing the needs for strong backup plans. Equipment risks like design flaws, aging infrastructure, and equipment failure can cause critical system breakdowns, especially in key components like pumps and digesters. People-related risks include poor safety practices, human error, and inadequate training, which can lead to operational mistakes and safety hazards. Management risks like lack of oversight, poor safety policies, and outdated risk assessment can jeopardize the operation's safety and efficiency. Finally, let's discuss the impact of risk in anaerobic digestion system, focusing on measurement, materials, and external factors. Measurement risk like inadequate monitoring and data inaccuracies can lead to poor decision and system failures. Material risks such as variability in feedstock quality and contaminants can disrupt the digestion process and lower efficiency. External factors include regulatory changes and market dynamics can which can bring new compliance demands and affect operational stability. Managing these risks is key to maintaining effective anaerobic digestion operations. Risk assessment matrix for anaerobic digestion potential risk. A risk assessment matrix helps in identifying, assessing, and managing risk by categorizing them based on their likelihood and severity. In the catastrophic category, risk like major biogas leaks and risk to surface water and groundwater have very high severity and likelihood, needing immediate action. The major category includes risk like accidental fires and diffuse gas emissions with a likelihood ranging from medium to high. These have significant impacts but occur less frequently. Moderate risk like harmful gas emission and design flaws are more likely but less severe. Finally, minor risks like noise and vibration have the lowest impact and likelihood but still need monitoring to avoid escalation. The matrix helps prioritize which risks require the most urgent mitigation efforts.
Next, in the fourth part, we will talk about risk mitigation strategies. Here, we will explore comprehensive strategies to mitigate risks related to human health and safety, risks related to design and operation, and risks related to environmental impacts. First of all, we need to apply operational best practices to mitigate the risks related to human health and safety. Developing and implementing standard operating procedures, SOPs, for all operational aspects, including feedstock handling, system maintenance, and emergency response. SOPs provide clear guidelines for operators, reducing the risk of human error and ensuring consistency in operations. Training is another key component. Regular training for staff on SOP, safety protocols, and emergency procedure ensure they are well prepared to handle any issues that may arise. Maintaining records in the form of skill training matrix is recommended. Personal protective equipment must be mandated in certain areas, such as where manual is stored, which you can see in this picture. The operator must be certified in its use with equipment fit testing and medical clearance according to OSHA regulations. In terms of design and operation, there are several strategies to mitigate the risk of anaerobic digestion system. Regarding the input material, we need to control the quality of feedstock by performing regular testing. Testing can help to identify contaminants such as heavy metals, toxic substances, or pathogens present. Contaminants disrupt the microbial activity necessary for effective digestion, leading to reduced biogas production or even system failure or malfunction. And third, it helps us to decide whether the feedstock material is acceptable to proceed in the AD system or not. If necessary, the feedstock must undergo pretreatment using mechanical, thermal, or chemical methods to eliminate contaminants and pathogens. Retreatment also makes the organic matter more accessible to anaerobic microbes, improve digestibility, enhance biogas production, and overall system stability. Regarding the plant system design, use corrosion resistant material to ensure the system longevity, prevent gas leaks, especially in critical components like piping, as hydrogen sulfide generated can speed up corrosion and cause spills. Proper equipment design and installation, implementing safety valve or pressure relief valves to control overpressure, as well as following technical standards and guidelines from relevant authority, including municipal and provincial government, help prevent catastrophic failures such as gas leak or equipment explosion. From the perspective of process monitoring and control, install automated monitoring systems are critical for tracking key processes parameters such as pH, temperature, biogas reduction, and feedstock loading rates. This system provides real-time data, enable operators to make in-time decisions, and promptly address any deviations. Set up alarms and alerts for critical parameters to ensure immediate response to any issues such as methane leaking, allowing for quick corrective action to prevent minor problems from escalating into major issues. Include redundant system and sensor that are as backups in case of primary system fail. At the same time, develop contingency plan to deal with any unexpected scenario that impact operational control and safety. Moreover, establishing preventative maintenance, which means monitor equipment conditions, inspect and regularly maintain equipment to minimize breakdown or malfunction during operation, and it can help identify potential issues before they become significant problems. With regard to immediate safety measures, it is ultimately important in an anaerobic digestion system due to the risk of hazardous gases such as methane and hydrogen sulfide. Gas detection system and proper ventilation are essential to prevent the accumulation of these gases that could lead to explosion and health hazard. Use explosion-proof equipment and electrical fittings in areas where flammable gases may be present. Ensure all equipment used are certified and meet safety standards. Fire suppression systems are also another important safety measures. It is necessary to train all staff on how to use them in case of emergency. Another aspect to mitigate risk is through technical and technological innovations. Responsible authorities should fund research and development to drive continuous improvement and innovation in AD technology. Keeping up with the latest technological advancement and upgrading systems as necessary. The third aspect is mitigating the risk of AD system relating to environmental impacts. Ensure regulatory compliance and obtain all necessary permits, prevent legal issues and potential fines, staying up to date with regulatory changes and maintaining accurate records and evidence for ongoing compliance. In fact, poorly managed digestate can lead to nutrient runoff, contaminating soil and water sources, and disrupting local ecosystem. Therefore, it is necessary to continuously monitor environmental parameters to understand and assess the impacts of AD plant and apply in-time corrective actions, such as proper containment, tracking emissions, or treating digestate. This is the end of our presentation, and thank you everyone for watching this video.